PyTorch tutorial. In this section, I'm going to talk about how to build neural nets of machine learning with PyTorch. Okay, this PyTorch is based on Python interpreter, and you can download it. PyTorch. Okay, you go to PyTorch homepage, which is pytorch.org. It's like saying that it's main library of TensorFlow. PyTorch has some big industrial backing behind it. So, for example, Facebook's AI lab is one of the research laboratory uh, promoting this PyTorch. You can go ahead and import these following packages and visit pytorch.org to get PyTorch installed on your machine. By the way, I'm using PyCharm. You can also download my PyCharm version is 3.7 2018 version. You can type in your terminal pip install touch etc. And you can also download the Torch Vision. The version is 0.0.6.0 minus F for the switch, and you can download in this homepage here. Then you can take a look at in PyCharm. You can go to the setup settings, and you can go project interpreter and see you have two library installed, Touch and Touch Vision. Okay. Also, you have a nice PyTorch tutorial, Korean tutorial. If you go there, at the homepage at the bottom here, if you take a look at this PyTorch example, there are some many examples, but I picked this one. This is much easier to understand. You get make underbar moons classification data from sklearn by typing import numpy as np, and from sklearn.datasets import make underbar moons. And you can also use that from sklearn.model underbar selection import train underbar test underbar split. And also you download your nice plotting library, which is import matplot library dot pyplot as plt. So the plt is the keyword later. And you can import torch, and you can also import torch.nn as nn. And you generate data by using those commands over there. So here x and y give you a nice xy coordinate of data, which actually makes something like a positive set and negative set. Okay, so it's like a waveform, like a tag shape. Okay, and you also have this noise 0.2, okay, included in the data set, 500 of them. And as you see the comment over there, sharp split into test and training data. So we have training data and test data for both x and y position. Okay, so in the xy plane, you can it's two-dimensional data, so you can use that test size at 25%. Okay. Okay, continuing example, we get this make a moon classification data from sklearn. Okay, we already did that, and you need to take a look at by using PLT command plt.figure and plt.scatter and plt.title, and finally you show the data. So here purple dots and yellow dots represent positive and negative data sets. Okay, so it's scattered between minus 1.5 up to 2.5 for X data, and for Y data is scattered also from minus 1 to plus 1.5, etc. Okay, so we need to do some small and clean classification task, not complex one. So this is just tutorial. So sharp, we have a comment, define network dimension. So our number of input dimension is over there. Xtrain dot shape number 1. And sharp layer size. For hidden layer, we have a 4 hidden layer. The output is just 1 because we are just separating 1 and 0, positive set, negative set. So it's like a binary classifier. So we have only one output unit and 4 hidden units. Okay, and you need to, as the next step, you need to build your network. So the command is net equals to nn dot sequential bracket. We have a input layer which is linear, and ELU exponential linear unit, and we have also fully connected layer linear. The number of hidden layer is 4 and the number of output unit is 1, and after that we have a sigmoid function, very simple one. Now this print command, print net, will show you that the structure, network neural net structure over there in the red box. Here 0, 1, 2, 3 is the number of index of the layer. It's very simple. Okay, now our next step is to define a float tensor in PyTorch and pass the values to get the prediction. Okay, so this is just an example. X equals to torch dot float tensor, and we have a 1, 1, and net X will give you the response in the red box over there, tensor bracket 0.5764 grad func fn equals to sigmoid backward. It means sigmoid backpropagation. Okay, and if you have GPU, then you can make this computation speed fast. So to learn this on your GPU, if you have CUDA installed. Right now the CUDA version is 10.2, but my computer doesn't have this one right now. So there is an option that you can download depending on the version of the CUDA. So here you use that 3-line command instead of the above 2-line commands. Okay, net.CUDA brackets x equals touch dot float tensor bracket 1, 1 dot 2 device equals to apostrophe CUDA. Okay, and net x. By doing this, you can take a look at this red box response. Tensor, the same thing, bracket 0.5764. Device, we have a GPU, which is apostrophe CUDA colon 0, and the same gradient function, which is sigmoid backpropagation. So here we have to tell the network to use the GPU by calling the CUDA method. then define the device for our tensor. If you don't have a nice GPU, then there is an option that you don't need to use CUDA. Okay. Next type, ready to train by defining the loss function and optimizer. Here we define loss function, which is from the library, Torch library, and then dot BCE loss brackets, and the learning rate is 0.01. You can initialize. An optimizer is defined by this torch.optim dot adam. So this is an adaptive gradient method with the momentum. Bracket nets the parameters, brackets, comma, LR equals learning rate, which is 0.01. Okay, so we only the binary cross entropy loss. This BC is that represent binary cross entropy. This loss function and its learning rate needed to set our optimizer. Okay, so that we can initialize our optimizer in the algorithm. Now we train this binary classifier. We just need to loop over our data set a few hundred times until it converges. Typically, training up into, we break this training by using mini batches, usually 128, sometimes 64, and make our predictions, outputs, so to speak, and we calculate loss and update the network all in one pass. Okay, here is the code example in when we train a binary classifier. Here we have some initialization on top. For example, train loss equals brackets. Train accuracy is brackets. Iteration, the number of total iteration, 1000. Y train underbar T, which is from our torch built-in function, torch.float tensor, Y train dot reshape -1, comma 1. So in this case, we have a positive set and negative set, okay, for the labels of Y train underscore T. Now, I is the iteration index for I in range of iteration from 0 to 1000. Oh, I think this is integer. And X train underscore T, which is from the same torch built-in function, torch dot float tensor X underbar train. So this X underbar train underbar T, which is our data, two-dimensional data. Y hat, which is the net X train T. So you compute this Y hat as prediction value. Actually, this is the output. And you compute the loss by using loss function Y hat and Y train T. So Y train T is the true value, and Y hat is our estimated label between -1 and +1. Okay, and we have a loss dot backward and optimizer dot stop, optimizer dot zero gradient. Here, this is some kind of backpropagation routine. So your Y hat class is NP, where Y hat detach dot numpy is less than 0.5. Okay, so this is Y hat class value. You find the accuracy by computing this built-in function np does sum. So Y train reshape if it is the same as y hat class, then we say they are accurate. Okay, which is divided by the total number. Okay, so that the accuracy is between 0 and 1. Now we have a train accuracy dot append accuracy and train loss append loss dot item, and then the following commands, following statements are how to plot the training loss function and actual validation loss function is probably later. And we have a accuracy function plotted here also. Okay, and finally plt.show will give you the figure. Okay, let's explain the code example of training a binary classifier. Okay, number one, PyTorch doesn't take NumPy arrays directly, so need to pass those values through the torch.float tensor function first to convert it to the proper format. It's similar to the function in the MATLAB, which I have denoted with those some variable name underscore t for clarity. This is new variable. With your GPU, just add dot to bracket device equal to semicolon CUDA to the end of this command. Okay. Second, after computing prediction and loss function, call point. What I mean by is dot backward brackets method on the loss tensor itself. This tells PyTorch to compute all of the gradient for our network. Okay, for backpropagation. Number three, tell the optimizer to dot step brackets forward, which applies those gradients to updating all of the weights and biases in the network. So this is updating command. Next, zero out all of the gradient, essentially throwing them away so that we may apply the new gradient after the next iteration. So by doing this, you can clear the temporary scratch pad registers memory, so to speak. And number four, to log our data, you will notice we call point detach bracket method on our prediction y hat. We do need do this to tell PyTorch to remove the graph structure from this value, meaning that we no longer want to calculate derivatives with these values. Okay, so you can save some memory. Okay, here's the result of training. Our network trained over 1,000 iterations, and this iteration is epoch, and pushed this classification accuracy toward 90%, but not exactly 90%. It's almost 0.87 or 0.88, something like that. So we have two graphs. On top we have a training loss function. It goes down, approaches to 0. And the next figure is training accuracy, starting from somewhere 0 point something to almost 0.9 in this case. Okay, this is visualization of the classifier with the test set. We apply test set, and in this case we get accuracy 0.87 in this case. So here, take a look at purple dots and yellow dots, and because of this tag mark, we have some positive false, which is false positive, so to speak, which is yellow dots, and false negative, which is purple dots in the area of yellow region, which is maybe negative region. On top we have a positive region, probably. So we have this curve, hyper curve over there, actually separate those binary for those binary classification. Okay, this is how you make your code in order to get the previous regions, and positive set, negative set, purple dots, yellow dots. Okay, this is hard to look at, so I'm going to briefly explain and make it fast. First, we pass test data, 5 statements of that, and we print some test accuracy. Okay, and then we plot the decision boundary and determine grid range in x and y direction. Okay, by using that x min, x max, y min, y max, and we set grid spacing parameter, and the spacing parameter is computed from the previous one, and we create grid, and then we concatenate data to match input, and then pass data to predicts method by using touch.float tensor data, and then we use again the net function, and then we have a reshape of that xx dot shape. Okay, and then plot the result. Plot plt dot figure, plt dot contour f built-in function, and plt dot scatter, excuse me, etc. By doing this, you can visualize those regions, boundaries of correctly classified ones, binary data, and false positive and false negative, etc. Now, continuing our PyTorch example, we need to improve our accuracy. So one simple way to improving this accuracy is we need more learning cycle, or we need more parameters. Sometimes we need more hidden node. To implement an object-oriented approach to building and training these networks, we much easier to adjust. To run this on a GPU, set the device argument to CUDA. First, run it with the default settings to show the result match what we saw above. So we have a 5 statement net, which is network x comma y. So here network is some kind of class that actually perform our job, and print net.net to take a look at the how the net structure looks like. Okay, so it's in the red box over there. Okay, sequential bracket 0, 1, 2, 3 layers. Okay, and the net the train, this is actual training process. Net.plot training result. This one actually plots the results, and net.plot testing result. This one also tests the result by using our trained parameters. Before I show you the code itself in improving our accuracy, I'm going to show you the training loss function and training accuracy together. In this case, we have similar response as before, but we have different graphs. Okay, when you improve the accuracy, we have still we have 4 hidden nodes, I believe, and we have a false positive and false negative over there, and the yellow dots are false positive and purple dots are false negative in this example, so to speak. The accuracy becomes a little bit, it's 0.87, and every time you perform the simulation, the accuracy will be a little bit different, but in the same range. Okay, finally we have this code in Python, actually PyTorch library included. We define our class network bracket colon, which we have bunch of definitions. Okay, initialization and the building network, and if you have CUDA, then initialize CUDA. And here we have a network structure, the same as before. Self.net is the variable. And also loss function is defined, self.loss function. And self.optimizer, which is touch.optimum.adam, same thing, same as before. Okay. Okay. Continuing the code, we have a bunch of definitions. Actually, these are functions: predict, calculate loss function, and update network, which actually does this backpropagation routine and optimizing in the computation, and calculating accuracy function. And also we have a training function, and the number of iteration is 1000 as before. If you take a look at the for loop at the bottom, we have the same routines. Okay. Also in plotting, we have functions, plot training results, and plot testing results. So for training data and for test data, we do this. We are using those two functions. Okay. And finally, we have this other during the plotting. We have set grid spacing parameter, and we create grid, and we concatenate the data to match input, and we pass data to predict method, etc. And finally, we have this figure control scatter the data and show command to plot the result. Okay, when we improve our accuracy, now we increase the number of hidden nodes gradually. As you see in the program, 1, 5, 10, 25, 50 node. So take a look at how we adjust the hidden node and change our results. But here we have a main program over there. So we have a for loop, n goes from 1 to 50. So 1, 5, 10, 25, 50. So see how the false positive and false negative changes. Okay. Okay, so here, if you have one hidden node, it's just a linear line. So we have 84.8% test accuracy. So we are using test data. Okay. Now, if n is 5, the number of hidden node is 5, then we have test accuracy 92.8%, a little bit increased. And then the number of nodes is 25, then we have test accuracy 95.2%. And as you take a look at this line, hypercurve, separating positive set and negative set, it's a little bit complex right now. Okay, it's like some hyperbolic function, okay, cubic hyperbolic function. And then finally, if the number of hidden nodes is 50, complex enough, then our test accuracy increases up to 96%. So here, if you take a look at the false positive, we have only one false positive over there, the yellow dot on top, and below that we have 4 false negative dots, the purple dots, okay, in the yellow region. Okay, so by increasing the number of hidden nodes, you can improve the accuracy, both training and validation. Okay, we have this PyCharm virtual Linux environment. Okay, here I have some example of the previous tutorial. Okay, let's expand this. We imported the NumPy and sklearn.dataset as a make moves, and sklearn.model selection. We import as train test split. And also we imported this plotting library as PLT. And also we import torch and torch.nn as nn. So nn is the keyword in PyTorch functions for neural networks. So here we have a random seed initialization process and preparing data. And then we split data into test and training data here. And then we plot the binary classifier system, the raw data, and the title is moon data. And we also define network dimension and layer size. The number of hidden units is 4, number of is 1 as before. And also we build our simple network, okay, and print net characteristic, okay. And here we have, I don't download the GPU version of Torch, so it's a CPU version. But here, I'm going to use this Torch float tensor. Okay, this is to check if it's correct. And we define our loss function, running rate 0.01, and define our optimizer, Adam. Okay. And initialization with the iteration number 1000 maximum. And we use this data structure, Y train under T. And real iteration, actual iteration goes here. Okay. And plot again, plot our loss function and the accuracy together. Okay. And we do test by using X test set and Y hat comparing. We evaluated the accuracy of test data. Okay. Here, continuing. And plot the result. Okay. Let's execute this program. Okay. Before I execute, we have a homepage here, PyTorch here, and you can go get started. But anyway, we have you can download it. It depends on your program and software. If it is Linux, then you can click here. The build version is here 1.5 in Torch library. Okay. And I am using Windows 7 so right here. And you can use Conda or PIT or Live Touch or Source. Here I pick PIT with Python. And CUDA, if you have a GPU, very nice GPU, the up-to-date GPU is right here. I selected none, but and you can run this command here. This one, cut and paste, and go to your PyCharm terminal. Clicking this, here I have my project folder, and you can uh, Here you can cut and paste like this, and after you can get the right installation going on and on. Okay, I'm going to quit because I already installed. And you go to the settings, and project interpreter. Then you will see two libraries here. I have TensorFlow. Torch 1.5.0 version CPU and Torch Vision 1.6.0 0.6.0 CD version. So I have downloaded it and already installed. Okay. Here, let's execute this example. Okay. Okay, I have executed this one. Then, as a result, you can see the raw moon data. Okay, this purple that's positive sets. This yellow dots, they are in negative sets. Okay. Continuing, I have this nest structure, sequential, with 4 layers over there. Okay, we have training loss function and training accuracy. Training loss function, training accuracy. In approaches, the accuracy goes about 0. Where is it? 89, probably in this case. Okay. Alright, let's get rid of this. 0.87 here. Okay, test accuracy. By the way, the training accuracies should be higher than test accuracy, of course. Here I have this positive set, negative set, and we have false positive, false negative. Okay. Alright. So I think it's finished. Okay. Okay, let's terminate this one. Something wrong. Okay. And the next PyTorch program example was to use this by we want to improve accuracy. So I want to change the number of hidden layers by using this class, okay, class network as before. So here initialization, same as before, and we have a different definition of built-in the functions in this network with different method here, similar to this. Okay, and then we change the number of hidden nodes from 1, 5, 10, 25 up to 50. So let's take a look at how it really works. Okay, so here, executing this program. I have raw data here, same as before, a little bit different because of noise, 20% noise. Okay. And I have a net structure over there, same as before, with how many hidden node? Just one, okay? And here, I have training, loss function, training accuracy here. So here, training accuracy approach is about 0.89 or something, okay? Here, okay, 0.87 was test accuracy with this as before. This is for just checking if it is correct, okay? And now the hidden number of hidden nodes is 1. I have test accuracy 84.8, which is a little bad. It's not that good. Okay, here false positive, false negative. Okay, just linear, just line. Hyperplane. Okay, and if number of hidden node is 5, then you get a little bit better, almost 92.8%. Okay, in this case. Okay, so you get this result. Okay, so here we have a little bit complex curve, hypercurve. Okay, separating positive and negative sets as a binary classifier. And then we have a number of hidden nodes, 10 of them. Okay, so here we have 10. Curve is a little bit different with 94.4% accuracy, validation accuracy actually. Okay, so I have 1, 2, 3 false positive and 1, 2, 3, 4 false negative. Okay, now oops. Okay, we have by the way, that was when the number of the hidden node is 10. Right now, I have number of hidden nodes, 25 of them. Right now it's 25 of them. And the test accuracy is 95.2%. We have 1, probably 2 false positive, and 1, 2, 3, 4 false negative. So curve look like it's okay. And then the number of hidden nodes is 50. Okay, the last one. Let's take a look at it. Alright, so we have 50 hidden nodes. False positive 1, false negative 1, 2, 3, 4. So it's much better. So the test accuracy is 96%. Alright? Okay. That looks good.